Okay. And I'm glad the participants can hear me. We'll switch to our honored guest in just a minute. So I'm going to get started. This is the February meeting of the Wenatchee chapter of the Ice Age Floods Institute, known as the Erratics, a wonderful name. And I am Ralph Dawes, and I'm going to just introduce things and then introduce our guest. And every other month on the second Tuesday, we'll have more guests giving wonderful geology presentations in coming months. So the next one will be in April and so on. And then by invitation, we have for tonight, our speaker is, and I think you can see him as I speak, but our speaker is Dr. Rob Thomas of University of Montana Western, which is in Dillon, Montana. And here I got to go sideways and just give you a little more. I have a connection with Rob. I've known him since graduate school in the geology department at the University of Washington. And while we were there, we both overlapped in helping to teach the field methods class in geology that seniors in geology majors there in their senior year or so. It's kind of a hard course to pass sometimes. But anyway, it's a capstone course for the geologists there to get their degrees. And they teach the field methods course from the University of Washington. I think they're still doing that. Is that right, Rob? Yes. Out of Dillon, Montana. They go over there. It's a wonderful place, Dillon, Montana. And so I know from personal experience, from being with Rob and from knowing him beyond that he's a great guy, a great geologist, and a great teacher. And also, he has of late co-authored and been a force behind getting out the new and updated and beautiful editions from Still Mountain Press, I think, of the Roadside Geology of Montana, a big, beautiful book with the color maps and everything. And also the Roadside Geology of Yellowstone Country. So I think people here, are Yellowstone fans. And if you go there, you got to get that book. That's my pitch. So without further ado, here is Rob Thomas, Dr. Rob Thomas, to speak about the geology of Yellowstone Country.
Great. Thank you, Ralph. It's great to see you. Thank you for the invite. And I am going to attempt to share this screen on my end. So Ralph, let me know how that works for you, okay?
Okay.
It shared, hold on, it shared whiteboard. There we go. Okay, can you see my desktop, Ralph? Oh, Ralph, your mic's off.
Sorry. Yeah, we see your slideshow.
Okay.
Not yet in full screen mode, but we see.
All right, so I'm going to do that right now. How's that?
Perfect. Do you have a cursor highlighter?
Yes, I do. Can you see the cursor?
Yes, we see it. Okay, I'm going to be quiet now.
All right. Very good. All right. So thank you so much for joining this evening. It's great always to talk about Yellowstone. As Ralph mentioned, my introduction to the geology of Yellowstone started with field trips with the University of Montana. I did a master's there, and the geology field camps during the summer and running students through the park. And then the University of Washington, Ralph and I and others, Marley Miller and many others, did field camps as teaching assistants. And we ran trips through the Stillwater and over the Beartooth and into the park back then. And since then, I ended up at the University of Montana Western in Dillon, and I started working on projects related to the periphery of Yellowstone, the Yellowstone hotspot tract, in particular looking at deposits of ashy lahars that define the ancestral Missouri River system during Miocene time, mostly mid-Miocene to earliest Pliocene. And the work was centered on understanding how we could use these old deposits off of the Yellowstone, the track of the Yellowstone hotspot and the thermal bulges to reconstruct the formation of basin and range topography in Southwest Montana. So I'll be addressing that here momentarily, but the take home is that Yellowstone's played a big role in the formation of the basin and range in Southwest Montana, and is largely responsible for the most recent northwest trending basins and ranges in Southwest Montana, which are now, we know from datable materials, about 4.5 million years and younger in age, which is an astonishing change from where we were just a few decades ago, and thinking that the mountains and the valleys that we see today had been present since Eocene time, 40 plus million years ago. So nothing could be more further from the truth. All right, so let's go to Yellowstone. And I feel the best way to discuss the geology of Yellowstone is to give you an overview of the geological history of the region of Yellowstone, not just the park and not just the volcanic piece, but the whole thing from the Archean to the present. So hold on to your seats. Here we go. All right. Well, of course, Yellowstone has over the years been in the news, and the Discovery Channel made a movie about what it might look like if the Yellowstone volcano were to erupt. And of course, they always kill the geologist, and some survived, but the geophysicists were killed off. And that it was a pretty accurate portrayal of the mechanisms in play, and I'll go over those. But it's important to recognize, and I get this a lot teaching classes, that people, worry about the Yellowstone caldera and living so close here in Dillon. And it's a very low probability event. Yes, there have been 3 eruptions over the last 2.1 million years, and there's about a 600,000+ year interval between them. But any statistician will tell you that 3 data points don't make a very good line. So the bottom line is that it's a very low probability. I always tell students you're much more apt to be killed in a back alleyway in Butte, Montana, than you are in an eruption of Yellowstone. No offense, of course, to my good friends in Butte, Montana. All right, so on the left here in this NASA photograph, this is the Yellowstone volcanic plateau. You can see Yellowstone Lake here, and you might notice this circular object right here. That is a caldera, part of the 3 calderas that make up the Yellowstone volcanic plateau. And we'll go into that in detail later. My house is right off of the map right about here. So we are alarmingly close to the hotspot in Dillon, Montana. All right, so let's go way back and talk about what we see in the whole region. The rocks, the oldest rocks in the Yellowstone region are very old Archean rocks. They're part of what's called the Wyoming province, or the Wyoming Craton. They're part of the old Craton of North America. the old core of the North American continent, Laurentia, and they date back to over 3 billion years in age. And some of the rocks have zircon crystals in them that have dates on them of 4 billion years, making them some of the oldest dated materials in the United States. And so these are extremely old rocks. They're well exposed in the greater Yellowstone region and the Tetons, shown in the photograph here on the left. And of course, in the Beartooth Mountains to the northeast of Yellowstone National Park, and in the Absaroka Mountains, which is between Livingston East and north, between Livingston rather and Gardner, Montana. A lot of people enter the park going down the Paradise Valley, and the rocks on your east side, a lot of them, not all of them, are these old metamorphic rocks. Sorry. Okay, so these rocks are metamorphosed. They were crushed and heated in continental collisions. There were multiple collisional events throughout this period of time, and with the last big one being about 1.8 billion years ago. We call it the Big Sky orogeny. And the Big Sky orogeny resulted in a large block of rock called the Medicine Hat Block colliding with and suturing to the Wyoming block, or the Wyoming craton or province, whatever term you like. And so these rocks have been through multiple metamorphic events, and they are mostly high-grade metamorphic rocks, lots of granitic gneiss and other high-grade metamorphic rocks. All right, a supercontinent formed by about 800, slightly before about 800 million years ago, and it started busting up, called Rodinia. And when it busted up, as is common, it was associated with the injection of liquid rock that has the composition of basalt, which you all know well in Wenatchee. Basalt is a type of rock that comes from partial melt of the mantle, where you're partially melting high temperature minerals. And you get a rock filled with calcium-rich plagioclase and pyroxenes. These dikes, which are called diabase, which just means the crystals are a little larger because they injected in the subsurface, they represent this extensional event that occurred with the breakup of this supercontinent, shown here on the Ron Blakey map, about 780 million years ago. So this dike right here, which is on Mount Moran in the Tetons, represents the breakup of Rodinia and the intrusion of mafic dikes made out of basalt or gabbro, as a result of extension. Okay. All right. Now, all of these metamorphic rocks and igneous rocks from the Precambrian time were eroded essentially down to a relatively flat surface across most of the region. And there are exceptions. There is some topography during that time. But for the most part, the big mountains had been there and eroding for a long time, and they were essentially eroded away. And by the Paleozoic, which is between 542 to 251 million years ago, MA stands for mega annum, which means millions of years ago. Sea level rose up, and it covered this relatively flat surface in North America in shallow tropical water. You can see here is north is pointing this way, and this line is the equator. So you can see that Yellowstone National Park was very close to the equator during this time period. So this water that was covering the region was not only shallow on the continent, but also warm and tropical. And it supported a variety of tropical marine life that was just starting to evolve in large numbers and diversity at that time, what is referred to as the Cambrian explosion. And and I know that well because I worked on a lot of these sections for my PhD. I studied Cambrian trilobite mass extinctions. I studied mass extinctions. Trilobites were the organism I focused on. This is a tail, or the pygidium, of a trilobite right here that I collected just outside of Yellowstone Park near Cook City. And it's in a tropical marine limestone made out of little balls of calcite called ooids. And these ooids formed in shallow, agitated marine waters some 500 million years ago. And there's some remnants throughout the region of Yellowstone from this time period. And my favorite, if you're going to go to the area, is Beartooth Butte. This is this photo right here. Beartooth Butte is on the Beartooth Highway from the northeastern entrance to Yellowstone Park and up over the Beartooth Highway. And so as you're headed up the Beartooth Highway, you pass Beartooth Lake campground, and just pull in there, and there's a boat launch, and you get a spectacular view of Beartooth Butte. And what Beartooth Butte is a Cambrian down in here someplace, sitting on the Precambrian metamorphic rocks, this gigantic unconformity, rocks that are 3 billion years in age, overlain by rocks that are 520 about 520 million years in age. So a gap in the rock record of nearly 3 billion years, hence the great unconformity, long period of time of erosion, non-deposition. And then sea level rose up, as you can see in the graphic, and it deposited these tropical marine deposits. And the seas went in and the seas went out, and this goes from Cambrian to Devonian at the top here. That's the Jefferson Dolomite. And what's really cool is this red dot. The red dot is the Beartooth Butte Formation, and it's a time when sea level dropped and a channel was scoured into the underlying marine limestones. And then sea level rose back up, and it deposited estuarine and eventually fluvial deposits in the channel scour that had been made. And that particular spot is loaded with the fossils of a plated armored fish that lived at the time, some fossil insects, and some of the oldest vascular plant fossils known in the United States. I am embarrassed to admit that I have been actually on this slope. As the disclaimers say, don't try this at home. Okay, as we go out of the Paleozoic, and the seas are going in and the seas are going out, and these sediments are accumulating on the eroded basement, everything starts to change in Mesozoic time. What happens is there's a supercontinent at the time called Pangaea, and Pangaea, all lands, breaks up. And as it breaks up, it's forming the Atlantic Ocean. It begins the formation of the Atlantic Ocean. And it takes the North American plate and it moves it in a westerly direction, where it collides with proto-Pacific ocean floor out here. And ocean floor being more dense than continent, it subducts underneath it. So this diagram shows that right here. Here's what's called the Farallon Plate, Pacific Ocean floor, subducting and descending underneath the continent of North America. As it descends, water is released, and that water lowers the melting temperature of rocks that are already very hot, and it creates magmas that through a variety of processes become very silica rich and erupt to form stratovolcanoes like the ones that you know in your backyard in the Cascades. So like Mount St. Helens, Mount Rainier, etc. And those were located in westernmost Montana and Idaho at this time during the Mesozoic, from the Jurassic and into the Cretaceous, primarily in the Cretaceous. When plates collide, the rocks get folded. So all those Paleozoic and some of the Mesozoic rocks that had previously been deposited, they got folded and they got thrust faulted, meaning they got pushed from west to east. And so in our part of the world, these rocks around Yellowstone of this age are all tightly folded, and older rocks have been shoved up over younger rocks, forming what we call the fold and thrust belt. And as all this sedimentary rock piled up, it depressed, in part, it depressed the continent, and sea level was very high, and it was inundated by shallow water. And here it is. This is the Cretaceous Interior Seaway, or what we call the Western Interior Seaway. And this seaway linked up the Gulf of Mexico with the Arctic Ocean. And Yellowstone National Park at that time, say about 70 million years ago, was located right on the edge of that. And there are deposits in the park that contain dinosaur fossils. If you know the park at all, Mount Everett's, which is near Mammoth, is a place where you can see these rocks of the seaway. Some of them are marine, some of them are marginal marine. And again, dinosaurs were living along the margins of that interior seaway. All right, and the volcanism and the active volcanism and the folding and the thrusting are going on out here to the west of that area. All right, so there's some spectacular deposits in the Yellowstone region, from this period of time that were deposited in this Foreland Basin in the interior seaway. This is one of my favorites, the Chugwater Formation. It's Triassic in age, and it's a tidal deposit, non-marine to tidal deposit. And then it's overlain by this white layer called the Gypsum Springs Formation, which is gypsum deposits. And the lighting on it's just spectacular. It's a spectacular unit from this deposition along the margins of the seaway. All right, by the Cenozoic, say 65 million years to the present, but in particular from 52 to 40 million years ago, there was a major outbreak of volcanism in the Yellowstone region. It is related probably to the continued subduction of the Farallon Plate underneath North America. Only it created a widespread area of volcanism throughout Western Montana. There are various names in the region: Chalice Volcanics in Idaho, Dillon Volcanics near Dillon, Lowland Creek Volcanics near Butte, the Central Montana Alkalic Province throughout Central Montana in the Bears Paw, Highwood Mountains, etc. And the mother of all of them, the Absaroka Volcanics in Yellowstone and up into the Gallatin Range, all the way up towards Bozeman. And these were big stratovolcanoes. They were like your volcanoes in the Cascades, high, steep-sided, andesitic, dacitic volcanoes, highly eruptive, very explosive, generating not only a lot of ash, but a lot of lahars, which those of you who are old enough to remember or have read about the Mount St. Helens eruption, it's like the Tootle Creek lahar that occurred during the eruption in 1980 of Mount St. Helens. And what these lahars do, if you look at the map, these centers of volcanoes are shown as the little red circles here in the Absaroka Belt, in the eastern Absaroka Belt to the western Absaroka Belt and the Gallatin Range Belt. And these are areas where there were actual volcanoes, and we know that they were there because there's volcanic neck deposits, the interiors of the volcanoes, kind of like Devil's Tower. And so we can see those. If you know the park, Bunsen Peak to the south of Mammoth is an example of the neck of one of these Eocene 52 to 40 MA volcanoes. So that's the guts, the interior of the old volcano. The thing that's most commonly preserved in the region are the lahars, because the lahars are slurries of mud and water and debris that go down the river valleys off the volcanoes. So they're going into the topo lows, and they tend to get preserved as a result. And what they carried with them was an incredible amount of vegetative material. The Eocene was a tropically warm time in Wyoming and Montana at the time. And so we had trees that included bald cypress trees, redwood, and a whole range of different kinds of vegetation that reflected the altitudes. So you would have different kinds of trees growing on the sides of the volcanoes than what were down in the lowlands. And when the lahars would be generated, they would go down the river valleys and carry all of the vegetative debris from the higher elevations down through to the lower elevations. And so we have a very good idea of what the flora, the paleoflora looked like from Eocene time as a result of the fossil forests of Yellowstone. The photograph on the right is a Texan who's not used to high elevations and very uncomfortable here with the altitude, standing next to two trees on Specimen Ridge, which is a wonderful place to visit in the Lamar Valley. And these two trees were possibly buried in place. There's a lot of debate over it, whether they were buried in their growth position by a lahar, or whether they were carried in the lahar and buried in the upright position. Remember, a tree has a root ball to it, and the root ball is full of rocks. And in a very viscous flow, like a lahar, that tree is going to move down that lahar, carried in an upright position because it's like a bobber in a viscous flow, and the weight is on the root end of it. And so it can be transported and deposited in the upright position. Just because those trees are upright does not mean they were buried where they were growing. That's my point. And I think that the evidence is clear that both occur in the Absaroka volcanic rocks, but just please know that both can occur and do. Okay, now these volcanic rocks of Eocene age were really for a long time not recognized as different from the volcanic rocks that formed in the calderas that make up the Yellowstone Plateau volcanic field. It really wasn't until the 1950s that radiometric dating was being utilized by a graduate student at Harvard and later by the great Bob Christensen to distinguish these old volcanoes that have nothing to do with the hotspot and have everything to do with the Farallon plate subduction from the hotspot volcanic rocks that are in the caldera and outside of the caldera in the park. So that's a relatively recent recognition. At least I think it's recent. It was in the 50s. So not that far back. Okay, now to my stuff. So we get into the outbreak of the Yellowstone hotspot about 17 to 4 million years ago. And what it does is it creates a large thermal bulge around the outbreak point. And off of that thermal bulge developed the ancestral Missouri River system. And we have been working out the details of that river by studying their deposits in Montana. So this photograph on the right shows a humongous ashy lahar. It's about 75 feet thick. It's sitting on a paleo soil, so it's not even in the channel. It's on the floodplain. And it is 75 feet thick on the floodplain. This was a bad day. We call it You Bet Your Ash. It happened 10 million years ago. It came out of the one of the calderas on the Snake River Plain that is today on the Snake River Plain. And it flowed down the ancestral Missouri River and probably ended up in Hudson Bay, somewhere in the northern, in Canada, because that was the flow path for the Missouri at that time. That means that all the extensional topography that's in the way, like the continental divide here between Idaho and Montana, was not there at that time. And these deposits go up to about 4.5 million years ago. So all of the northwest trending topography in southwest Montana has developed in the last 4.5 million years. For those that know the area, the Beaverhead Mountains, the Tendoy Mountains, the Blacktail Mountains, the Sweetwater Mountains, and the Tobacco Root Mountains all have components of them that formed in the last 4.5 million years as the plate moved over the hotspot, creating this track. And by the time it got to about right here in the Heisey volcanic field 4.5 million years ago, the stress directions around the thermal bulge changed and it popped these northwest trending normal faults that then terminated that old flow path of the ancestral Missouri River. Okay, so I hope that makes sense. The old ancestral Missouri River emanated off the thermal bulge 17 million years ago. It held that northeast trending flow path until about right here, 4.5 million years ago. And then boom, these northwest trending normal faults created new basin and range topography that were raised in the path of the old drainage, and it created the modern drainage we see today, which is a combo of those two drainage patterns. Okay, all right, to the volcano. So by the time Yellowstone got to or the hotspot, remember the plate is moving this way, hotspot stationary. So by the time the plate is here, where the Yellowstone Plateau volcanic field is, there are 3 eruptions that occur that make up the Yellowstone Plateau volcanic field. And they started about 2.1 million years ago. There's one at 1.3, and there's one at about just shy of 0.64. So 640,000 years ago. And what it's doing is it's uplifting the area out in front of it. So the Beartooth Block is going up as a result of this thermal expansion around the hotspot bulge. And the Gravants and Absaroka Mountains of Wyoming are going up around that. And it's also affecting the rate of extension down to the south in the Tetons and over here in Montana in the Centennial Mountains and other faults in the region around the Dillon area, which are very active and have some of the highest uplift rates, frankly, on Earth. Okay, so to the volcanoes. So the biggest of the eruptions was the Huckleberry. It erupted a tuff called the Huckleberry Ridge Tuff, and that occurred 2.1 million years ago and put out 600 cubic miles of ejected material. Okay, and that, of course, is a low number because that's based on what's preserved. 600 cubic miles of material. By comparison, Mount St. Helens ejected 0.1 cubic miles of material. 0.1, not 1, 0.1. So we can relate to Mount St. Helens, many of us. This eruption is catastrophically larger than stratovolcanoes like Mount St. Helens. There's nothing else like this. This is, the largest explosive volcanic eruption on Earth that's preserved. And it's not alone. So that the second eruption is at 1.3 million years ago. That formed the Island Park caldera, and it's 67 cubic miles of material. And then the intermediate one of the three is the one that formed the last eruption, or caldera forming eruption, at 640,000 years ago, give or take. And that's 240 cubic miles of material. So these three eruptions of Yellowstone are not comparable by anything else. Krakatoa, Mazama, Mount St. Helens, they are like nuclear explosions to a firecracker. The ash distribution is huge. The state of Texas from the eruption 2.1 million years ago would have been covered in several feet of ash from the eruption. This is a huge volume of ejected material. And it was going on over the entirety of the transect of the Yellowstone hotspot. So the big ashes, you bet your ash, that we have in the Dillon area is then not surprising. Why these big water laying lahars? Well, when you form a caldera, that's a low point and it can hold water like Yellowstone Lake. So if you rupture the wall of the caldera during a subsequent eruption, that water might be released with all the ash that's coming out during the eruption and create a slurry of ash and water, a lahar, that then traveled during Miocene time down that ancestral Missouri River drainage. Could it happen today? Sure. Could go down Paradise Valley, could go down the Snake Jackson Hole, down the Snake River drainage. It could go down the Clark's Fork of the Yellowstone to the due east, potentially. Okay, so let's look at the hotspot. So I love the whole discussion over Yellowstone hotspot. It is not something that is completely, set in stone. There are two camps out there. Some people think that the Yellowstone hotspot emanates from a shallow depth somewhere at in the upper part of the mantle, and other people think that it is emanating from great depth, possibly down there around the core mantle boundary. There's a group out of Durham in the UK. They're the shallow people, and there's the group at Utah. Bob Smith, historically working on that, and they're the deep plume people. So this diagram you're looking at is a deep plume model constructed using seismic tomography from the group graduates of the group out of Utah. And this red area, red always makes it look worse, is you can see extending down to a depth of 500 plus kilometers. And it is extending and deflected at an angle, not straight down, but to the north west. And I always like to point out to students that the hotspot emanates right below Dillon, Montana. So if you're to drill a hole, we could get down to the deepest parts of the Yellowstone hotspot plume, if indeed it is there. But again, it's a debated thing. All right. As you get towards the top of this gigantic plume, if it is, through the mantle, the gabbroic magma that is in the mantle is rising up and resting and pooling up against the bottom of the lithosphere. And as it pools against the bottom of the lithosphere, it is incorporating the granitic minerals, the minerals of the granitic rocks of the continent of North America. And it's changing the composition of that gabbroic magma to something that is more granitic in nature, more silica rich. And so there's a pool of magma down there that is being fed by gabbroic magma that is altering its composition through a variety of processes, some of which include the melting of the lithosphere to create this silica-rich magma. Okay. And that's happening at a depth of about 10 kilometers or so depth. All right. So how does the caldera itself form? Well, what happens is the magma that I just showed you will dome up the overlying brittle rock of the lithosphere. And because it's brittle, it's going to crack. Those cracks that form become conduits for material in the magma chamber to escape. What's happening is you're thinning the lithosphere and releasing pressure. So it's like a bottle of Coke. It's under pressure, and if you slowly remove the pressure by twisting the cap off the bottle, it's going to allow for some of that magma to volatilize and gas escape and some liquid to go with it. And when that liquid comes out and it hits the surface coming out of these fractures, it turns to glass. So these droplets of liquid are they're being expelled out of the magma chamber at a high velocity because of the pressure they're under, because of all of the gas. And they hit, that liquid droplet hits the surface and it turns to glass. That is being shot into the atmosphere to great heights, well into the stratosphere. Okay, so we live in the troposphere, so it's going way up into the stratosphere where the volume of all this material and the weight of it cannot be sustained. So what happens is it collapses down on itself and it squirts out in all directions. Those are called pyroclastic flows, fire rock flows, and they're moving at hundreds of miles per hour, and they're carrying temperatures of thousands of degrees Fahrenheit, and they incinerate everything in their path. And the sediment that is deposited, the unit that's deposited, that falls out of the sky from it is called tuff, volcanic tuff. So, the volcanic tuff then squirts out and can go for tens of miles away from the caldera. The Huckleberry Ridge tuff, for example, we can find almost to Ennis, Montana, which is a good 80 plus miles away from the edge of the caldera at that time. So they can move a long ways. And again, that's a bad day when that happens. All right, so this is not some big explosion out of the ground that creates a hole. What happens is all the eruption of this material that forms the ash sorry, it's very delicate. It forms the ash. It leaves a void in the top of the magma chamber, and that void will collapse. And that is the caldera. So the hole that is generated is actually a collapse feature that's formed by the eruption of a lot of ash out of the top, out of the top of the magma chamber, leaving a void that then the overlying lithosphere collapses into. So the surface collapses, it creates a caldera, and then these fractures in the caldera become conduits for the lava that is in the magma chamber, which is really silica rich, to come out and flow out onto the surface. And those are the rhyolite flows that fill in the caldera in Yellowstone National Park. And they did not flow like what you see in Yellowstone. Sorry, in Hawaii. They don't come out of the ground out of a fracture and flow away from that vent. They instead actually underplate. They come up underneath the vent, and they just add to the pile on the underside of the pile. And the pile rises up, and the pile is hot and viscous and like Play-Doh. And it reaches a point where it can no longer hold that dome of material that is coming up from underneath, and it starts to spread out like a plate, like bread dough, out in all directions. And these then filled in the caldera, flowing in some places tens of miles at a rate that probably was so slow you could not even see it, right? Time-lapse photography would have been needed. All right, over here on the right, of course, is a pyroclastic flow in the Philippines. This truck probably doesn't stand much of a chance. Yeah, but these are the kinds of clouds of ash, gas, rock fragments, phenocrysts or crystals from the magma chamber, glass, that were squirted out during the pyroclastic flows, and they will make tuff. All right, so here's the eruptive history. This is a map from the book, and it shows the three calderas. Here is the outline in purple is the Big Kahuna. That's the Huckleberry Ridge Tuff Caldera at 2.1. And here is the 1.3 caldera at Island Park, just a little fellow. And then in red, here's the outline of the Yellowstone caldera 640,000 years ago, roughly. In yellow shows some of the welded ash flows or pyroclastic flows or tuffs expelled from these eruptive events. And again, here's the NASA photograph of the area. And you can barely, you know, if you were to show this to a friend, they would say, what are you talking about, volcanoes? I don't see volcanoes. And it's because of this, right? That the way in which the caldera forms and the fact that so much of it is filled in with rhyolite. You can see the Island Park caldera here. See it? It really pops. And it's filling up with basalt. So it's in this transitional stage from rhyolite to basalt, and it'll turn into the Snake River Plain eventually and get completely buried in basalt and be hard to see. But for now, it's a wonderful teaching tool because it's a transition from the active caldera and rhyolite to the Snake River Plain where the calderas are buried in basalt. And here you go, this one's in between. Caldera margin still visible and basalt filling it in. All right, eruption one, my favorite, the Huckleberry Ridge Tuff. This is the Golden Gate on the right. Many of you have been there. That is Huckleberry Ridge Tuff. There it is over there, okay? In between is the Gardner River. And that is a major cut. This was the topo low 2.1 million years ago, this pyroclastic flow. All that topography has been cut in the last 2.1 million years. That is phenomenal. These two connected, likely, and they've been eroded out. We don't know for sure because it's gone. But in the rocks behind me, it's continuous across, which would suggest it should have been continuous across here as well. When you look at it close up, this is what you can see from Mammoth, looking across at Mount Everest. You see airfall ash in white down here at the bottom. That's the very beginning of the eruptive phase. So the caldera is starting to, it's doming. The ground is doming, and those fractures that are forming are expelling some ash. And that ash is falling out of the sky as airfall ash, like snow falling out of the air. Then that column of ash that goes up to the stratosphere cannot hold that any longer. It's called the Planaean column. And that Planaean column just comes crashing down on itself and squirts out. And when it squirts out, it's carrying this hot material, which is pumice and rock fragments and ash and phenocrysts or crystals that were in the magma chamber. And they're all coming, hugging the ground at a very high rate of speed, carrying very high temperatures, so hot that when they hit the ground, they baked the ground. These are Cretaceous shales, and they baked them. And you can see that contact metamorphic bake zone right here in red. And it turned to glass when it hit the ground. That's called a vitrophyre, and you can see it's slightly black on the bottom. And there's a honest to God obsidian on the bottom of the Huckleberry Ridge tuff. Then within the tuff, you can see there are layers, and the layers reflect pulses of pyroclastic material coming out of the Planaean column and squirting out. So this didn't all just happen at once. It happened in multiple pulses, but it probably happened over short periods of time. Weeks, probably, but not all at once. All right, eruption 2, Mesa Falls tuff, 1.3 million years ago. This is over in Idaho, gorgeous place to visit. Got to go there, and the geology is spectacular. So near Ashton, Idaho, you can see this pyroclastic flow deposit, the Mesa Falls tuff. And ashy, you can see pieces of pumice all over the place in it. These are gigantic pieces of pumice here near the top of it. It's not as welded or compressed and hard as many of the other pyroclastic flows, probably because it's smaller, much less thick, sorry. And it is now filling up with basalt. So in the distance here, you can see there's the Centennial Mountains. On the other side is Montana. Thurman Ridge is the outside rim of the caldera, and Garrett basalt is what's filling in the caldera. So Thurman Ridge is the edge of the caldera. This is inside of it, and it's filling up with this rock, basalt, which you can see is a nice scoria in this particular outcrop, full of gas bubble holes. And the Mesa Falls go over resistant layers in this infill in the caldera. The last eruption, Lava Creek, 639,000 years ago, is the one that made the active Yellowstone caldera that we know today. And it created a pyroclastic flow just like the previous two eruptions. That is called the Lava Creek tuff. And you can see it really well along the Lewis River on the south end of the park as you're heading out of the park down towards Tetons. And it's exposed along the road as well. It's also exposed real well near Madison Junction, just down the road as you're heading towards Norris Geyser Basin. But this is all in the roadside book. You can follow it. And so here's a close-up, and you can see I was talking about phenocrysts. You can see little crystals here. These were early form crystals in the magma chamber that got expelled with the pyroclastic flow and then encapsulated into the pyroclastic flow. Some of these are rock fragments, others are pieces of pumice. And then the matrix, the ground mass, is ash. for the most part. Typical tuff, pyroclastic flow deposit. And this one is welded. You can see what I meant by welded is you can see these pieces of rocks and pumice are squashed. So this was really hot when it was deposited, and it got compressed and squashed and hardened. So this is a favorite building stone in the park. Many of the bridges and guardrails, these beautiful stonework that's in the park, that it's made out of Lava Creek tuff. It's the go-to rock for building stone in the park. All right. There are a bunch of other volcanic flows in the park, and many of them are outside of the caldera. They include basalts. This is the Narrows area near Tower Junction in the park, for those who know it. And this basalt has a date on it of about 1.3. Other basalt flows date also very close to the 3 caldera forming eruptions. So there's a basalt associated with the Huckleberry Ridge eruption. It's called Junction Butte basalt. It's 2.2 million years old, just before the eruption. There's the Narrows basalt, which is just a little older than 1.3, so just preceding the Mesa Falls tuff. And there's lava flows of basalt that precede the 639,000-year eruption that formed the Yellowstone caldera. These I call precursor, well, I don't, people call precursor basalts. What's happening is as the caldera is about to form, as it's doming up, the first thing that expels out the cracks is actually a partially melted mantle rock, basalt. And it comes out onto the surface, and it's very fluid, like volcanoes in Hawaii, and it goes down the river valleys. So notice this columnar basalt is sitting on gravel. It's sitting on outwash deposits, gravel deposits, stream deposits. Okay, it went down a river valley. And most of the basalts we see that are these precursor basalts that tell us that a caldera is about to form, they went down the river valleys. One of them went way down a river valley. The Junction Butte basalt, you can see it all the way as far north towards Livingston, Montana, in the Paradise Valley as around Immigrant, Montana. Okay. And then here's Obsidian Cliff flow. This is an obsidian flow. There's a lot of glass flows, both in the caldera and outside of the caldera. And what they represent is water concentration in the magma. These are very, very dry magmas, and they crystallize obsidian. And you can see that some of them are not crystallized, that are crystallized. These bands are actually rock, they're not glass. The dark areas are glass, the light areas are rock. So this obsidian, some of it is crystallized, and it will eventually all crystallize, because obsidian is glass, and glass is a liquid. And so eventually it will crystallize. We don't have a lot of old glass on the planet because it eventually crystallizes. These holes that you're looking at are places where there were gas bubbles, and then they get filled in with crystals, forming these beautiful little crystal-filled, like geode-like structures. All right. One of my favorite topics, and I know we're running shy of time here, so I'll try to get moving. We're almost done, is glaciation. So here's Pilot and Index peaks. This is the Matterhorn of North America, or at least of the US. And Pilot Peak is Absaroka volcanics, those Eocene volcanics, and was glaciated into this beautiful glacial horn during the last ice advance. That ice formed an ice cap over Yellowstone. You can see it in this graphic on the left. This is the Yellowstone ice cap. It had an outlet glacier that went down the Yellowstone River Valley, what we know as the Paradise Valley. and it stopped around Prey, Montana, for those that know the area. The Beartooth Mountains up here, they were covered with ice as well, and the caldera was covered with ice. And we think as much as several thousand feet of ice covered this area during maximum glacial. And what's interesting is something like this. This is on the canyon rim. So there's Canyon Village. It's about right there along the Yellowstone River, and it's up on the rim. And that block we can trace to the Beartooth Mountains. It's a piece of granitic gneiss that is over 3 billion years old that got plucked from a glacier up here in the Beartooths. So how in the heck did it get here to the Grand Canyon of the Yellowstone? Well, when deglaciation occurred at the end of the last glacial, the first ice to go was the low ice over the Yellowstone caldera. And so that left this open, and the glaciers flowed in off the Beartooth and dumped these rocks onto the rim of the Grand Canyon of the Yellowstone, and then retreated out as the glaciers went fully away. That's super cool to me. So next time you're in the park, look for the glacial boulders on the rim. You can drive right to this one. There's even a sign that says Glacial Erratic. And it came from Slough Creek up here in the Beartooths, and got deposited when the ice was removed over the Yellowstone caldera itself. So again, the ice goes away from the caldera first, and then it eventually went away from the Beartooths and surrounding high areas. All right. Hydrothermal explosion craters. Well, once the ice went away, there's a lot of groundwater in the region, and that groundwater is intersecting hot areas, and those can do a variety of things. And one of the things they can do is form hydrothermal explosion craters, or phreatic explosion craters, groundwater that explodes, expands and explodes. This one here is called Indian Pond, and it's near Fishing Bridge. And it's thought to have formed when an earthquake caused water in the lake to slosh away from this area, releasing pressure on rock that was hot, water, I should say, that was hot in the subsurface right here, and allowing it to expand and to literally, in this case, explode out. So these are explosions. They are not collapses, they are explosions out. And there's rock debris all over the place from this phreatic explosion crater, Indian Pond. Mary Bay, which is right here and covered by the lake, here it is right there. That Mary Bay is considered to be the largest hydrothermal explosion crater known. It also is thought to have formed when the water sloshed away from the area during an earthquake, what we call sashing. There's some strong evidence to support this, because there's tsunami deposits, lake tsunami deposits up here from the water coming back in during these events. Okay, hydrothermal features. The hot water percolates through rock, it picks up minerals and reprecipitates them at the surface. If you are outside of the caldera, the rock that is most available to you to pick up, if you're water, is limestone. Limestone's easier to dissolve. It dissolves it in this slightly acidic water, groundwater, and it picks it up and it comes out onto the surface. The carbon dioxide is released. That lowers increases the pH, and what precipitates out? Travertine, which is hydrothermal limestone. So outside of the park, like at Mammoth Hot Springs and Soda Butte, you have travertine deposits. When you are inside of the caldera, the hot water is mostly going through silica. It's going through rhyolite, which is full of silica. So what it does, it dissolves silica and it precipitates the silica as sinter, which is just hydrothermal quartz. So travertine outside of the caldera, sinter inside of the caldera. Now, that's not exactly always the case. Like everything in geology, there's some exceptions. There's a place near Madison Junction where there's a mix of both. You're in the caldera and there's a mix of both travertine and sinter. And so there are exceptions, but for the most part, most of the hydrothermal deposits within the caldera are sinter, quartz, and those outside are travertine. They picked up limestone. So it's what the hot water goes through. That's key. Those towers, those towers you're looking at are, they formed on the bottom of Yellowstone Lake and were part of a survey that was done by USGS folks and others. And some of these sinter towers were collected. So you can kind of think of them like Yellowstone's black smokers, only they're towers of sinter, of silica. Pretty cool. And of course, there's Old Faithful erupting at about 21 degrees below zero. And that's all sinter that is around it. The upper geyser basin, middle and lower geyser basin are sinter basins. Okay. Surficial processes. So once the ice is out, you have the ability for fluvial processes to start doing their thing. And let's go to this picture here. This is the Hayden Valley, and these beautiful meandering stream loops. Just love these, absolute textbook meander loops. They're carved in glacial lake deposits from Glacial Lake Hayden, which was there during one of the ice advances. And those lake deposits are important because the bison love them. They contain salts that they like to eat, and they are great to roll around in and dust yourself up so you keep the flies and the other biting bugs off of you. So whenever you're in the Hayden Valley, you might notice that the bison hang around in these areas that don't grow vegetation because they roll around in them. And those are lake sediments from Glacial Lake Hayden. You can see them in this wall right here. It's also really important because it's a place where grass grows well, so the bison like to graze there. And these soft sediments are a heck of a lot easier for burrowing animals to form dens than the hard rock of inside the caldera. So these lake sediments are places where foxes and coyotes and other animals that burrow have a tendency to like to live because they can. All right, now the Grand Canyon of the Yellowstone. Grand Canyon of the Yellowstone, we know, existed before the last two ice advances and retreats, because within the canyon itself are glacial deposits from the glaciers that occupied the Yellowstone Plateau. Now it's a little deeper than those glacial deposits because it's been excavating down through, but they're in the canyon, showing the canyon was there when it was ice covered. But when you look at the canyon from the air, it's distinctly V-shaped and so not U-shaped like a typical glacial valley. And what it reflects probably is the fact that ice over the top of a flat plateau, the Yellowstone volcanic plateau, is going to be stagnant. So it's not going to be very effective at scouring out a V-shaped profile into a U. It's just going to simply occupy the canyon, and it's going to maintain that V shape as a result. So we think that the ice over the plateau was largely stagnant, especially in the center of the plateau and over the canyon itself. So the canyon is a little older than glaciation, and the falls are forming where it is cascading over resistant volcanic rocks from non-resistant volcanic rocks. This flow right in here came out, 400 and some odd million years ago. And it filled in the Yellowstone caldera, and it went over a hydrothermal area like we see at Old Faithful. All that hot water from the hydrothermal area just kept percolating up through the rocks. And it turned many of the hard volcanic rocks into a clay soft rock. You can see the colors. That's more easily eroded. So the canyon was easily cutting through these soft hydrothermally hammered rocks. And then it hit these hard rocks that were not hydrothermally altered, and it formed the falls. Make sense? All right. The caldera is still going up and down. Bob Smith referred to it as a living, breathing volcano. And he's right. We know from measuring it from space that it rises and it falls, and it rises and it falls. And we also know that there's two areas that specifically, more than any other area in the park, have magma closest to the surface. So the Yellowstone caldera plumbing, if you can see my hand, it kind of looks like this. You have this deep plume going down to the mantle at an angle underneath Dillon. Then my hand itself, the palm of my hand here, is the magma chamber forming underneath the lithosphere. And there's two pipes that come off of that. And those are these two pipes of magma, one underneath the Sour Creek Dome and one underneath the Mallard Lake Dome. And they're domed up because of these two fingers of magma. Those are called resurgent domes. They're inside of the Yellowstone caldera. And they're areas where if you're looking for a place where you might get an eruption, in my view, it would be these two for an explosive eruption. We could certainly have more rhyolite come out anywhere within the caldera that just flowed along and didn't make a big fuss. But these two could erupt pretty violently because they are akin to the Mesa Falls Tuff, the Island Park area, that caldera, that little small one, which we think was a resurgent dome. Okay, so the magma is down there. You can see not too far in miles. Here's 3 miles down to well into the magma. There's 3 miles down to the bottom. So to the top of this finger of magma is only a mile or so from the surface. So there's magma pretty close to the surface. But most of the rise and fall that occurs in the caldera seems to be mostly related to water. The movement of groundwater around through the caldera along fault systems plays a big role in causing some expansion and some contraction. Some of it might be magma movement as well. All right, how do we know this is happening? Well, we've directly measured the rise and the fall of the Yellowstone region in modern times. And so over time, we've been able to actually, create maps that show uplift and subsidence of the caldera. But we can see it in the rocks too. This is the Lamar Valley, and notice these layers, these benches. Those are terraces. The Lamar River was once here, then it was once here, then it was once here, then it was once here. What does it show? It shows that the river is dissecting down through the ground, and the ground might very well be going up as a result. Okay? All right. Well, the area around the caldera is definitely still going up and dropping down, basin range topography. And we know this because in 1959, the largest magnitude earthquake in the Rocky Mountain region occurred, a 7.5 magnitude on the Hebgen Lake Fault and the several other faults in the region. And whoops. And they did a couple of things. They, one, caused a mega landslide. These are metamorphic rocks, and the landslide slid on these slick plains and these micaceous schists and blocked the Madison River, making Quake Lake. That happened the night of in August when when the rupture occurred in 1959. And it rolled up the side of the canyon on the other side and buried a number of people in the Rock Creek campground here under that slide debris, which you can see here. And it backed up Quake Lake. Hebgen Lake had a dam on it. The fault ruptured just out of view over here to the left. And this guy was the dam watch person. In those days, they had a person that kind of hung around the dam in a little shed, little cabin. And as the story goes, he was there. The earthquake occurred. He got, you can't stand up. It's shaking too bad. When it stopped, he took his flashlight and he ran out to look at the dam. He pointed his flashlight down at the lake. This is Hebgen Reservoir. The water was gone. And he thought, oh my God, the dam went out. So he went back up to his shack, he called into Ennis and told the sheriff the dam's gone out. He then came back down with his flashlight. He put the flashlight down and he noticed the water was coming back. And then all of a sudden he heard this sound like a freight train coming, and he decided he probably better get out of there. So he went back up to his cabin and he watched the water come and topple over the top of the dam at the level that he's holding his hand. It was a seiche. A seiche is a sloshing of water. It's like you're getting out of the bathtub and the water sloshes back and forth. What happened is the fault dropped the Hebgen Valley here down 25 or so feet on this side, and it caused the whole lake basin to slosh back and forth, and 4 feet of water went over the top of the dam many times, multiple times. Okay. What's the future of Yellowstone? Change. Another great story. I'll finish with this. 9:20 on my end. Whoops. Okay. So Bob Smith had a group of people on a field trip, and this is in Biscuit Basin. And they were standing here looking at this, and they were talking about how these hydrothermal pools, the hot spring pools, rarely erupt. They are, rarely erupt. It's not a common thing. And right as he said it, guess what happened? It erupted. So just as he's telling people that these hot pools don't erupt, this one erupted. And there was a fellow there that got pictures of it. I got a copy of this and put it in the book because it was just too good of a story not to share. But the point is, wait a couple of minutes and something new is going to happen in Yellowstone. Yellowstone is about change. It's an active volcanic center. It's a gigantic caldera, and it is about change. And if you're interested, you should tour around and take yourself a copy of Roadside Geology of Yellowstone Country. And with that, Ralph, I'm done and happy to answer questions.
Rob.
You're welcome.
Great. So I don't know if anyone could not get in, but if they find out about this later and see a recording, apologies. But
Okay.
but I think maybe just about everyone who wanted to get in, with maybe only a few exceptions, did, because we had a pretty good turnout, and people are still here. So questions. I think we can't hear.
You
from
can put
directly.
it on chat, and I don't know. You could maybe pick a few and ask me if you wanted.
Yes, we'll see. I mean, that was quite absorbing. We'll see if people have specific questions.
Yeah. They're not going to sleep tonight.
Yeah. Well, you tried to assuage them of their imminent supervolcano fear.
Yeah, no, they should be assuaged.
Except that last story. If you get too close, anything could happen.
Yeah, right. Watch the little ones, 'cause those are the ones that get you.
Yes. Who can see your message recording?
I see it, but
Oh,
that was
here's
just a
one.
thanks.
You see that question? How can obsidian be crystallized when it is dry?
Oh, okay. Well, Ralph is really the guy that ought to answer this question because he's the igneous guy. But I'll take a stab at it. Whoops! I'll take a stab at it, Ralph. And if I screw it up and you don't like it, you just tell me I'm full of baloney. And
Geologists are always doing that to each other.
all right, I'm going to go back to that. There we go. Just in case somebody wants to see a slide. So here's how I think, I like to explain it from the standpoint of a lay person. So the igneous rocks that you know of that have the largest crystals are pegmatites, right? And these are magmas typically that didn't cool like, super slow. And so they grew these large crystals, right? They have a lot of water. Pegmatites have a lot of water molecules. Well, those water molecules inhibit nucleation sites. And as a result, the nucleation sites glom onto all the elements that are going to make a feldspar crystal, for example, and you get a bigger feldspar crystal as a result of the presence of the water. Ralph, you okay with that?
Sure.
Okay. If you have a dry magma, you don't have those water molecules. And as the thing is hitting the surface and cooling, it's grabbing onto whatever it can to form a crystal, right? And if it doesn't complete the crystalline structure, then that by definition is glass, right? It doesn't have a crystalline structure. That's not a crystal, that's glass. Okay, now glass is a fluid. It's just a super viscous fluid. So eventually the elements are going to find one another to fulfill the crystalline structure and make crystals of quartz and feldspar. And so glass over time will eventually crystallize. But you can't explain obsidian cliff as a quick chill process. It's not like the glass blowing lab on campus. And the reason is this: it's thick, right? It's super thick. So it can't have come out onto the atmosphere and cooled quickly all the way into the interior of that flow. And it's glass all the way into the interior of that thick flow. So something else is at work. What is that? The inability to form complete crystals, probably because of the lack of water. That's my take.
Yeah, I like
Ralph,
that.
you okay with that?
I'm okay with that. Yes.
Okay, good. I'm a said paleo guy, so I defer to Ralph.
I did not know about the glacial history of Yellowstone.
Isn't that cool?
My wife was always paying attention to the igneous rocks when I was
there.
Yeah.
Isn't it cool? And the whole notion that the ice went away over the caldera first is really neat. We know so little about how the ice interacted with the geothermal features underneath. That is something that it really intrigues me, but we just don't have a lot of data on that. And it may have played a role in the going away of the ice more quickly than the stuff on the Beartooth. But most people argue, like Ken Pierce, who's the god of glacial geology in Yellowstone National Park, and I don't mean that in any way other than I believe it 100%. No one better than Ken, who recently passed away here in the last year. Ken was the person that argued that ice came in off of the Beartooth Plateau into the Yellowstone caldera because it was devoid of ice first. So as the Pleistocene ice was going away, I should say as Pinedale ice was going away during the last glacial max, as it was retreating, it retreated first over the Yellowstone Plateau, largely because it's lower topographically and doesn't catch as much moisture. The Beartooths catch much more moisture. that ice then remained and was still flowing. And once there wasn't ice in the caldera, the block was gone, and it was able to flow into the caldera and dump those big erratics of basement.
I'll buy it.
Yeah.
I'll buy it.
And the glacial deposits in the canyon prove, without a question, that the canyon preceded glaciation. This is something that, I've stood on Artist Point talking about the formation of the Grand Canyon of the Yellowstone and had people say to me, well, wasn't it all eroded out in a day? And I'm like, oh, here come the 6,000 year folks. Yeah. And it's like, no. And we know, and the reason is not because I'm being an arrogant, idiot. There's data. It was there during glaciation, and it's been further excavated, of course, but it was there during glaciation. So it's been around for quite a while.
Yeah, it's a great place for evidence around that relate to such debates.
Yep,
even though
sure.
Neither side will feel like they convinced the other.
Yep,
but that's fine.
Which is fine.
Yeah. I wanted to ask, okay, I've heard, have you been there? You've been there in the last few years, right? Like the Old Faithful?
Oh, yeah, I'm there all the time.
So because it used to be, back in the day, it had a shorter interval between and somewhat reliable. Yeah. Is that true? Is it longer or more irregular, or just generally longer now?
Yeah. Okay, first I'm going to say this. The thing that I know the least about are these idiosyncrasies about the thermal features. And here's why. And I'm going to get into trouble, and I'll just, if you start getting hate mail on the chat, let me know and I'll click off. And I mean it actually all tongue in cheek. There's a group of people that are obsessed with each and every thermal feature in Yellowstone National Park. I call them people call them the geyser geezers. And the geyser geezers are a wonderful group of people. They have their own publication, and they're a wonderful group of people that are passionate about details of how often, a geyser erupts, what the volume of water is that comes out of it. I mean, every little dirty detail, and over time, how it's changed over time. Nothing bores me more than that topic.
Well,
I'm a process person. I like to talk about why the geysers form and how they're different than hot pools, and fumaroles and mud pots, and how we get these different kinds of thermal features, right? That floats my boat. But these details about time and duration, so on, frankly, what I'm getting at is I don't know. I don't know the changes in Old Faithful, because it goes in one ear and out the other.
So you're not the one to ask, do I have time to run over to the concession stand and get an ice cream cone or a beer before it erupts again? So
right. That's now you're talking something I care about. Right? Is how long do I have to go to get an ice cream cone before it's gonna erupt? That's my top priority.
Okay. Well, that was my issue last time I was there, because they do have an ice cream stand there.
It's definitely changing. They're all changing, right? And they're so susceptible to change, right? You get a small change in the plumbing system, and it can change the everything, really.
Yeah. Well, it's like it's what you said. It's what who was it? Smith. Someone. It's a living, breathing thing. The whole caldera, the whole system.
Absolutely. Yeah, those changes are really, really, they're impossible to predict, right? What's causing them, when they're going to happen. They just do. One thing we do know that collectively is earthquakes cause major changes in the thermal features, right? So when there's a lot of earthquakes, they really affect the thermal features.
Oh, we do have more questions. Okay, sorry, I'm missing.
Yeah, it's okay. I've got time.
Because we have several. Are the basalt? Wait. So basalts, Brian. So basalts precede the big eruptions.
Yeah.
Well, then, if so, where will the next basalt flow occur?
I don't know. But there may not be another caldera formed. A lot of people are have argued that what's happened is we're transitioning from rift crust, thinner lithosphere, back to the west, right, to the southwest, into thicker lithosphere to the northeast, right, because we're going underneath the Wyoming craton. And what they're arguing is it might, like a blanket, snuff the hot spot out. So there is that school of thought that the hot spot is at its last point and it's going to get snuffed out. All right.
Okay,
I don't really even know how to evaluate that assessment, but it's some complex model argument that I can't evaluate because I just look at rocks. I've read those papers and the arguments are compelling that they make. However, if a new caldera were to form, it would be way down the road, right? The existing caldera is not even remotely close to filling up yet, right? It's still erupting rhyolite and filling up. It's not in its basaltic phase at all, which is the second basaltic phase, right? There's a pre-caldera basaltic phase and a post-caldera basaltic phase, which buries it all like the Snake River Plain. So where would it come out? Okay, I'll give it a shot. So the thing is progressing towards Billings, which I love, right? Because the plate's moving to the southwest, so the hot spot's going to the northeast, and it's headed towards Red Lodge and Billings, which won't happen in anybody's lifetime. And the major faults are the conduits for these materials to come out, right? So what you would look at are the faults. Let me see if I can get there. You would look at the faults out here in front of the caldera. Those are going to be the likely places for basalt to squirt out before a new caldera forms. Does that make sense?
So continuing the trend.
Yeah, continuing the trend.
Okay.
If it snuffs out, that's not happening. If it continues and the plate over time is moving this way, these fractures, these faults out in front of the hot spot, they're the places where the basalt's going to come out of the mantle melt directly to the surface and be able to come out uncontaminated.
Okay, great.
Because they're out away from the magma chamber itself. Make sense?
Yes.
And so they're getting away from being contaminated. They're skirting around it.
we need a model running. I mean, it's a three-dimensional thing moving forward.
I know.
Time, so
I know. We
okay,
do.
let's get. I mean, we're getting late, and I
Okay,
realize that anyone can leave when they want to. But Gary Provo asked. No, I lost it. About the basalt flows in central Washington, and how do they relate to the general geographic periods and plate tectonics of Yellowstone?
I don't know. And really nobody knows. I'm convinced nobody knows. I've been through every model because I had to write a book. So I had to read all of these papers. And I'm, of course, not the expert on that aspect of the thing. So I read them. Actually, I view that as a good thing, right? I read them as a general geologist trying to see, does that make a logical, reasonable argument? And what I think we know, we can see it here, right? So you're asking about, this trend of basalt over here, right? And all the way up and then you got the Columbia Plateau.
Yes.
Up in here.
We're still seeing, where's your cursor? Oh yeah, you're pointing way over.
Got it. Okay, so here's Boise, going up to Boise.
Yeah.
Right?
Okay, got it.
And there's Washington State, so there's the Columbia Plateau up here. All right, well, in my way of thinking, these are, I don't know, Ralph, correct me if the model is still back arc spreading, right? These are morb basalts, right?
they have a bit of a plume or an ocean island basalt signature.
Okay.
I mean, they are, yes, I mean, they're tholiites, but for
Yep.
specialty terms, but they have some helium isotopes and so on, at least in some cases,
Okay.
suggesting a possible deep mantle. It's not as strong as some other hotspots in the world, that
Okay.
signal.
Okay. Are a lot of people still in the camp of this being a back arc spreading area?
No, or they've complicated it by talking about tears in the Farallon plate and that sort of thing.
Okay, sure. That makes sense. And that's all good. Okay. So the question is, is this the outbreak point in the McDermott volcanic field about 16 and a half, 17 million years ago? I would say that based on the papers that the voluminous papers I went through, whoops, this thing's really sensitive, that the strongest evidence is that this is the outbreak of the Yellowstone hotspot. So that the track is that track right there. So that the hotspot has always been here, and that this was back there 16 and a half million years ago. Mm-hmm. And those are all collectively bound together without question. Right? They're geochemically connected together. They're geophysically connected together. The sedimentology piece I study connects them together. They're all connected together. This is the track of the Snake River Plain Yellowstone hotspot track. How this stuff relates over in here is beyond my pay grade. But that's the track of the Yellowstone hotspot to me. Okay. Now, you got these people that would have it going the other way too, right? Towards Oregon, towards the what the heck's the name of it? In Eastern, I'm having a brain block. Help me out, Ralph.
Wait, I was looking at
in Oregon, the volcanic center in Eastern Oregon.
Around Bend?
Yeah, around Bend, south of Bend.
Oh, Newberry volcano.
Newberry caldera. Thank you.
Yeah.
So, so there. I won't pick on anybody specifically by name, but there's a very good geologist who, wrote an article that was in GSA Today a number of years ago, connecting up the Newberry volcanic field with the track of the hotspot, and made the argument actually that the magma comes up underneath and then flows along the bottom of the basalt and then comes up on either end and progresses both to the northeast and to the southwest.
Yeah.
And you gotta love students. I presented this argument to my students in class, and somebody said, why doesn't it squirt out along the edges instead of at the ends? And I thought, that's a brilliant observation.
Okay, well, here's one. Maybe it's in what you teach in your pay grade, which is, did the so-called Yellowstone hotspot, does that cause the Cascade volcanoes?
No. Those are subduction zone volcanoes, right? From the subduction of the remaining plates, right? The Juan de Fuca plate. Do we still have a Gorda plate? Got the Gorda plate.
So that's a separate system.
Total separate system. What's interesting about Yellowstone, I'll diverge, is this argument going on between the Durham UK group and the Bob Smith group at Utah and his students who are now hither and yon. Whether it's a deep-seated plume that goes all the way down to the core mantle boundary, or whether it's the shallow thing that's just at the lithosphere, asthenosphere boundary. And I've paid attention to that in the periphery. I've actually written some articles for the group, the anti-plume group, and that is what they call themselves that. Mantleplume.org, the anti-plume people. And they make some pretty compelling arguments that Yellowstone's not a hot spot. It's a hot spot in that it's a concentrated area of large heat, right? But they believe it to be just a concentration of heat in the extension of the Great Basin.
Yeah.
And they've even argued it as a propagating crack, so that as the basin and range pulls apart, it's like taking a stick and pulling the stick apart, and there's a propagating crack down the stick that's allowing the magma to come out, progressing to the northeast. Now, I don't know what to make of that argument. I think it's fun and interesting. And it is true that the hotspot's right smack and dab in the middle of the basin and range extension. No question about it, right?
Mm-hmm.
But it sure has a lot of hallmarks of a stationary thermal plume that's deep-seated. And they've looked at some of the helium isotopes and some of the other geochemical tricks to try to see how deep. And those always get challenged by contamination and so on. And people always have a response to those data to say, no, that doesn't prove that it's deep. It could have been contaminated at shallow levels, et cetera, et cetera. So I don't really know what to think, and I didn't know what to think in the book in 2011. So what I did is I took it as an opportunity to teach science, and I presented both views of this and talked about how we, evaluate these ideas, and what the weak points were in both arguments and what the strong points were in both arguments.
Yeah, that's great, because I think in general, people looking in, it's not. It seems rather unresolved. Like there's
no question. Yeah, that it is still open. There's no question about it. Bob, one of the things, this is another piece about geology, I think that's important, especially high profile areas like Yellowstone. And I'll get in trouble for saying it, but I believe it's the truth. Don't think for a nanosecond that we scientists are just sitting in a cave someplace, with our test tubes doing very, very, accurate science with the scientific method. And we're not trying to make our case through marketing. Because Bob Smith at Utah had this model taken and put in National Geographic a number of years ago by a graphic artist that made it look so good that no one could ever argue against the deep plume model for the Yellowstone hotspot. It just looks too good. It was beautiful marketing. And whenever there was a chance to get into a layperson article, there he was, telling his story. And the folks at mantelplume.org, not there. So there's a certain amount of marketing that's gone into the deep plume model that has made it stand out in the public's eye as what Yellowstone is, even though there's some arguments against it. So marketing and sales is a part of what we do in the sciences.
Okay, maybe we're going to sign off soon. Here's one. Well, maybe I don't have the name, but how does the Yellowstone hotspot relate to the Hawaii hotspot on the Earth? Well, it relates if they both go down to the core mantle boundaries. What I'd say.
Correct. Yeah.
What do you think?
Yeah. So yeah, I mean, what's interesting, there's a number of oceanic hotspots around the globe, right? And there aren't very many continental hotspots, which is a problem for the Yellowstone hotspot being a hotspot, meaning a stationary plume that has a deep origin in the mantle. And so, as Ralph just said, the connection is that depending on who you buy, which geophysical group you buy, they share being deep plumes in down near the core mantle boundary, coming up stationarily, mostly stationarily, and having the plate move over them, creating a track of volcanic eruptive deposits. And so they shared that. One comes up through ocean floor and comes out as tourist lava, and the other comes up through continent and gets contaminated by gas and silica and is, life limiting for the human species if it happens to erupt.
Okay. Yes. Great. Okay. Well, we didn't have to answer all the questions, but we're going to. So last one.
Okay.
Do you think there's a so instead the caldera being low or maybe being hot may
Yep.
have caused that glacier there to melt early? But what about the caldera and the volcanism? Could that have set off ice ages or at least glaciations there in Yellowstone? Does
That's a
the
great
timing work
question.
out?
Yeah, that's a great question. There can be no doubt that the eruptions of the calderas over the track of the Snake River Plain resulted in long periods of cold on the planet as a result of ash circulating around in the atmosphere and blocking out the sun. This is not an area I'm an expert in, but Rampino, for example, at NYU has done some work on how long a period of time the sun might be blotted out and how long we might go without a growing period if a caldera level eruption were to occur. And we're talking decade plus. Now, would that precipitate a glacial episode? It appears not, because we know the timing of these big caldera forming eruptions that you see right here really well. And they're not associated with glacial events. So no, they don't do that. But do they cool the planet down significantly and cause some extinction of organisms? There can be no doubt.
Great. All right. Well, that I think answers all the questions for all us hardcores who stuck it out.
Yep.
But no, this is fascinating. I mean, that's just a wealth of neat things you get from thinking about and going to Yellowstone.
Oh, it's such a great place. Yeah, it's one of the things that I like the most is the rate of uplift and down cutting. When you go to the Gardner River and you stand there and you're looking at Huckleberry Ridge Tuff over there on the other side of the Gardner River, and you're looking down in that deep canyon of the Gardner River, which is, I've forgotten the exact depth, but over 1,000 feet. And you're like, oh my God, that tuff is Pleistocene. And all of that excavation has occurred in the Pleistocene. It blows you away. It blows you away. It just gives you a sense for how incredibly rapid the rate of change, how rapid changes in the greater Yellowstone region.
Yes. That's probably not the bumper sticker they're going to make Yellowstone. It blows you away.
So. I like that. It blows you away. That's great. I think you're onto something, Ralph.
Okay. All right. Well, I want to thank you again, Rob. This was wonderful to have you. Thank you for.
It was my pleasure to be here. Yeah.
And yeah, and a lot of people stuck around. So
okay, great.
I'm going to end it now.
Okay. Well, thank you very much. Good to see you.
Most welcome.
See you,
anytime. Come by Wenatchee sometime.
Will do.
Okay.
Okay.
Bye-bye.
Dapper light.
Okay. All right. I'm going to sign off. There's more of us left unless anyone throws in one last question. Nope. Okay.
Great. Thanks, Ralph.
All right.
Yeah.
Bye-bye.
Okay.